What if we got rid of zero moment points and capture points and used something else? No, I'm not suggesting that we dispose of ZMP and capture points, but in a previous video, I basically suggested throwing out the entire concept of dynamic stability for bipeds and replacing it with what I call gait or balance fragility. If we did that, how might we practically measure gait fragility, and how would we use that in a feedback controller to reliably balance on two legs? We'll try to answer the first question in this video and deal with the other question in a later video. All papers mentioned and referred to in this video are linked or listed in the description below. So take a look. All right. So I've asked you to consider discarding the entire concept of dynamic stability when thinking about bipedal balance and locomotion. But if we do that, how exactly would we measure this thing I call gait fragility? Let's start by defining gait fragility: a vulnerability or sensitivity of one's walking to uncertainty and disturbances, an elevated inability to ambulate as desired in the presence of perturbations or risk. I introduced this concept of gait fragility as an alternative to the popular objective of dynamic stability in bipeds. Then I offered center of mass controllability as a potential candidate as an inverse measure of fragility, but never really suggested a quantitative measure of fragility itself. In this video, I'll talk about the related concepts of capturability, viability, and controllability, review some of the literature on how manipulability ellipsoids can be applied to bipedal balance, and end by proposing my own simple fragility metric: capturability, viability, and controllability. According to the paper Capture Point, A Step Toward Humanoid Push Recovery by Pratt and others, a capture point can be described as a point on the ground at which a biped can place its foot to come to a complete stop. Using simple models, such as the linear inverted pendulum model, one can compute such points and bring the center of mass to a stop by stepping on one of them. This capture region can be defined as the set of all such points, and an in-step capturable region is the set of all points for which a biped can take n or fewer steps to bring its center of mass to a stop. Obviously, larger capture regions suggest an improved probability of maintaining balance, and capturability-based frameworks have been used to develop effective gait controllers. Zaytsev and others observed that the capturability framework could be considered a special case of viability theory, which is concerned with a controller's ability to avoid failure from a set of initial conditions. Using simple two-dimensional models, they presented results that suggest two ideas. First, they asserted that viability, roughly defined as the ability of a biped to walk without falling, and controllability, the ability of a biped to reach a specific target location, are equivalent in most cases. In other words, the ability to move one's center of mass to a specific location is equivalent to being able to walk without falling, and vice versa. Second, for most local targets, if the biped was able to reach the target, it was able to do so within 2 steps. Their conclusion was that attempts to compute in-step capturability beyond n equal to 2 are likely unnecessary. When considering these concepts of capturability, viability, and controllability, we observe that they are generally characterized as regions in the state space that a biped should seek. While one could potentially quantify the relative size of such regions with respect to the larger reachable state space, these frameworks and definitions are global in nature. For example, the objective might be to determine an exact measure of viability, even with data that might not be available online for the robot. In addition, these definitions and frameworks do not relate as easily to our fragility concept, for which we would like to define a local online metric: center of mass manipulability in bipeds. A related concept is that of manipulability ellipsoids, which have generally been used with respect to fixed-base robotic manipulators. As you can see in this figure, in the planar case of a simple two-link manipulator, the set of potential end effector velocities is bounded within the ellipse. In 3 or more dimensions, this shape is considered an ellipsoid. Narrower sections of the ellipsoid denote that the end effector is limited in its ability to move in such directions, while longer areas of this region represent the ability to move in those directions at higher velocities. The Jacobian J relates joint velocities to end effector velocities, and can be used to determine how long the ellipsoid region is along its various axes. Let E be equal to the product of the Jacobian transpose. The eigenvectors and eigenvalues of E are the principal axis directions and the squared lengths of the principal semi-axes as shown in this figure. Naksuk and Lee proposed the zero moment point manipulability ellipsoid as a combination of the ZMP balance metric, the manipulability ellipsoid representation of robotic manipulators, and the dynamics of humanoid bipeds. The ZMP manipulability ellipsoid represents the area in which the biped can instantly move the ZMP, and as is the case with regions of capturability and viability, larger areas suggest a greater ability to recover from imbalances or disturbances. In earlier work on whole body humanoid movement, the same authors defined center of mass manipulability using the concept of manipulability in robotic manipulators. They referred to their manipulability metric, W, as the balance maneuverability measure associated with current posture Q. W is equal to the square root of the determinant of the center of mass Jacobian multiplied by its transpose. As is the case with robotic manipulators, this value is proportional to the area or volume of the manipulability ellipsoid and serves as a proxy for ellipsoid size. However, the authors asserted that the horizontal span of the center of mass manipulability ellipsoid, which relates to the horizontal maneuverability of the center of mass, is more important to bipedal balance than the value of the above metric. They illustrated this horizontal span with a dotted line on the ellipsoid, as shown in this figure. Yet they did not offer a value representing or proportional to the horizontal span of the ellipsoid as a potential manipulability or stability measure. In their work on the use of ankle push-off for improved balance in a three-dimensional biped simulation model, Kim and Collins used several measures to interpret their findings, among which was the use of the condition number of the center of mass controllability matrix to give a sense of how easily the biped could respond to perturbations. By center of mass controllability matrix, they were referring to a controllability matrix as one would construct for a linear system like x dot equal to ax plus bu. The difference here is that they only used the center of mass affected portion of the linear system rather than the entire system. The condition number of matrix E is often seen as a representation of error sensitivity in manipulability for end effectors, as in the textbook Modern Robotics by Lynch and Park. We provide the general equation for the condition number next, where E is defined as shown earlier in terms of center of mass and is not for a manipulator end effector. The center of mass condition number is equal to lambda max of E divided by lambda min of E, where lambda max and lambda min are the largest and smallest eigenvalues of E, and E again is equal to the center of mass Jacobian multiplied by its transpose. Note that the minimum value of the condition number is 1, and smaller values near 1 are desirable. A proposed fragility metric. The previous section ended with two manipulability metrics that come closest to the idea of fragility that we've introduced. First, we showed that the horizontal span of the center of mass manipulability ellipsoid is a simple measure of the horizontal maneuverability of the center of mass, which is the single most important factor for bipedal balance. Simply put, if one is able to maneuver one's center of mass as desired, balance and gait are less fragile. However, increased maneuverability is inversely related to fragility. That is, decreasing fragility as an objective means that one should increase maneuverability. So it would need to be modified to fit our framework. Second, we found that condition number of the center of mass controllability matrix gives a sense of how well a biped might respond to perturbations, which is related to our fragility concept. A lower condition number represents less vulnerability to perturbations, which corresponds well with the fragility reduction objective we've recommended. However, condition number is based on the center of mass controllability matrix. Roughly speaking, it's based on the principal axes of the ellipsoid represented by that matrix and does not take horizontality or verticality into account in its computation. Here's a simple metric that combines the advantages of these two metrics. Fragility metric zeta is equal to the maximum of the absolute values of z dot max and z dot min divided by the minimum of the absolute values of x dot max and x dot min, and the minimum of the absolute values of y dot max and y dot min. That's a mouthful. Here, z dot min and z dot max are the minimum and maximum values of center of mass vertical speed at zero horizontal center of mass velocity. X dot min and x dot max are minimum and maximum values of center of mass speed in the x direction at zero vertical center of mass velocity. And y dot min and y dot max are the minimum and maximum values of center of mass speed in the y direction at zero vertical center of mass velocity. We illustrate these values in this figure. This metric approximates the ratio between the vertical and horizontal spans of the center of mass manipulability ellipsoid, but it is conservative in that it uses the maximum and minimum possible values for the numerator and denominator, respectively. Since we desire larger horizontal spans and relatively smaller vertical ones, this is a check against unwarranted optimism in this metric, which we want to avoid for the fragility concept. Unlike condition number, this value can approach zero for very small vertical spans or relatively large horizontal spans. And unlike the use of horizontal span alone, the change in this metric corresponds to our sense of what fragility changes would entail. The metric can be estimated from local data and is easily computable online. Hope you enjoyed the video. In the next video, I will present a simple dynamic model of a planar robot that we will use as a test bed for comparing the fragility metric to these other balance measures. Thanks for watching.